This is Dr. S.P. Arsaf from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver my lecture 27 on the course of Strength of Materials, which is developed under the National Programs on Technological Enhanced Learning (NPTEL). Prior to start this lecture, I would like to refresh the previous concept which we discussed in the previous lecture. As we discussed, you see that if a beam is under the combined loads, like you see if we have the point load and the UDL, plus if we have that we have the UDL plus the triangular element, then how we can analyze those things. So in the previous lecture, you see that at which point the maximum bending moment is there, at which point the minimum bending moment is there, and what is the relation is in between the shear force and the bending moment. That kind of discussion which we made in the previous lecture, and we found that there is a point where there is a change in the bending moment diagram from positive to the negative. That means, you see, when there is a change from the sagging to hogging of the bending moment diagram, then this point is known as the point of contraflexure. Means, you see, we have the drastic changes there from the positive sign of bending moment to the negative sign of bending moment. So that you see we define, and even actually we found that at those points where the drastic changes are there in the shear force diagram, we found the maximum bending moment. So this kind of relations even we derived in the previous lectures, that when F is equals to dm by dx, then what exactly you see, whatever the changes are there in the bending moment with respect to the domain x, it gives you the shear force, and if we are keeping shear force 0, then the bending moment will remain constant, m will be constant, because dm by dx is equals to 0. So that discussion, you see, we made in the first part of our lecture in the previous class, and then you see we derive a simple bending theory, that with the certain assumptions, that you see when the beam has to be like the straight form, and the plane should be symmetrical towards the longitudinal axis, and also you see the plane should be remains plane before and after the bending, and whatever the material which we are using for the bending the beam material, it should be homogeneous isotropic material. So this kind of the assumptions which we made, and then you see we concluded that actually that if we have the straight beam and if we have the curved beam, there are certain portions which are unaffected by the stresses. That means, you see, when there is a straight beam, no bending moment is there, then you see all the fibers of that particular beam is just existed in the symmetrical way. But when you see a bending moment is applied at the two extreme corners, then you see the upper fibers is always experienced by the tensile forces, and the tensile stresses are occurring on those fibers, while the lower fibers, or we can say the bottom fibers, because it is just like the curved part, so the bottom fibers, you see, experienced by these compressive stress, the forces, or we can say we have the compressive stresses. But within those tensile and compressive, there is an intermediate layer on which there is no impact of this shear stresses are, and if we locus those points, if we just to find those the trajectory of those particular points, these trajectory or these locus is known as the neutral surfaces, and we can say actually whatever the axis which forming on these particular surfaces are known as the neutral axis. So neutral axis is that axis, you see, which you can say that whatever the impact is there of the bending moment, it has no impact on that particular thing, because there is no shear deformation, there is no deformation is there is no strain component is there all along this particular line, and that's what you see we define the neutral axis. And since it is a curvature path, so you see we define that actually if you want to define the radius, then always starting from the locus, this radius of curvature of the locus to this curvature path, so whatever the distance will come, that distance is known as the radius of curvature. So you see, now our reference point is this neutral axis, and now you see whatever the things will be going to happen with respect of the bending moment and all those things, our main focus will be there on the neutral axis, to define the neutral axis, and then correspondingly you see whatever the changes are there, we need to define. So that kind of discussion which we made in the previous lecture. Now you see in this lecture we are going to again you see analyze those things, that actually what will happen, you see, for if we have a different cross section of the beam, irrespective of, you see, if we have the rectangular cross section or I section or whatever, you see, then how we can find it out the neutral axis for those sections. First we'll also go for the numerical exercises, and then you see the key feature is that actually what will be the bending stresses in that, because till now you see we discussed only about the bending moment, that what will happen the bending moment, what will be the relation between the bending moment and the shear force diagram. So all those blah blah discussions which we made only with that shear force and bending moment diagram, still we didn't discuss about that what will happen when the shear forces are existing within the beam element, and then due to that what will happen with the bending stresses, or how they induce the bending stresses within those component, and then how these neutral axis will react when the bending stresses are there, and what are the potential area within the beam when it is under subjected by various forces, through which we can say that yeah, this is the potential area in which the maximum bending stresses are there, this is the minimum bending stresses are there. So if you want to design the beam irrespective of the cantilever beam or simply supported beam, you can simply focused on those potential area and use the factor of safety higher according to the safety reasons. So this kind of discussions which we are going to discuss in this particular first lecture. So first of all, as we discussed, the bending stresses in the beams or the derivation of the elastic flexural formulas, because you see first of all we need to see that how the bending stresses will form, and then how it will distribute all along the entire span of this beam. So in order to compare the value of bending stresses developed in a loaded beam, first of all we need to consider the two cross section of the beam like HE and GF originally parallel, because they are, you see, when there is no bending moment then they are absolutely parallel to each other. You can see the first diagram here on the screen, that these two we are taking these two elements in which these two lines are very they are simply parallel, this EH and GF, and you see these, as we discussed already in the previous chapter, that the middle section which is passing from the entirely this neutral surfaces, this is nothing but our neutral axis, and we just want to focus that actually if we take element, let us say from a distance y from the neutral axis, this AB, then what will happen means how the fibers will behave when it is under subjected by bending moment. That is our prime focus. So for that, again you see what we are doing here, since it is a plane structure in which this first figure 1a plane structure in which there is no bending moment, there is no shear, the forcing is applied, a straight beam is there well in means equilibrium manner, and you see for that we have a simple structure, there is no deformation is there, you can see on the diagram. But if when a beam is to bend, that means if a bending moment is applied, it is assumed that these sections remain parallel. That means you see H dash E dash and G dash F dash, they have to be there in the parallel, because our we assume that even the plane should remain plane even before and after the bending. So with that particular assumptions we can assume this kind of theory, and the final position of the sections are still together, the straight lines are there corresponding to the previous lines, and they also subtended by the angle theta, and you can see this particular diagram figure 1b as we discussed previously also, that when you apply the bending moment at the extreme corners, it will bend, and then you see the extreme top corner will be extended by due to the tensile forces and the tensile stresses are occurring on these particular surfaces. But you see this particular surfaces which is under the compression, we have the compressive stresses on this particular, but we have the neutral axis line, this A dash, this is the C dash and D dash, this there is no strain component on that. That means you see C dash D dash is equals to CD. Just keep this thing in your mind, because you see there is no deformation occurring along this particular line. This is the neutral axis is there. So C dash D dash, which we are denoting in the figure 1b, exactly similar to the figure this point CD in figure 1a. But there is a change in A dash B dash to AB, because you see the certain deformations are there, the extension is there. So we have the tensile deformation, and this is due to, you see we have a kind of some extension is there, and this extension we can easily form because we know that this distance is r, and you see this distance, because the neutral axis distance as we define that, we can always supposed to define the radius from this locus point to the neutral axis. So this distance is r, and also we defined in the previous section that actually this AB distance, this AB section has a distance from CD as a y. So this one is the y. So the total distance, if you want to find it out for the curvature path, is nothing but equals to r plus y, and then this theta is there. So we can define with the radius and arc definition for that. And then you see, like we have one more thing is that we have this h dash and g dash, which is also in the extensive part. So we have the maximum deformation in the tensile way on these particular points, and this is the minimum deformation at these point, like or we can say the zero deformation at this C to D point. And you see, like again the some compressiveness is there of this E dash F dash points in this particular figure. So these figures is simply justifying that actually whenever there is a kind of bending moment, then how like the fibers are playing in this particular way, and how the tensile and the bend, these compressive stresses are coming due to the bending only. So that's why you see we are saying that these normal stresses which are coming due to the bending action is always the flexural stresses. Now you see, consider the fiber AB of the material. You see, as I told you in the intermediate section, if you are just focused on the fibers of that particular path or the AB line at the particular distance y from the neutral axis, when the band will be stressed to A dash B dash. That means you see, now you see due to the bending action there is a deformation in this beam right from AB to A dash B dash. So now our main intention is that actually how the deformation can be measured and how we can relate this strain to the stress component with the using of, because you see the important feature here is whatever the deformation is there due to this bending moment is always the elastic deformation, and that is what you see we can straightway apply the Hooke's law for that, in which the stress is proportional to strain, and since here the bending moment is applied, so we have the bending stresses which is correspondingly like proportional to the strain component. So here with that particular theory, again what we are doing here, the strain in the fiber AB, which because our main focus is on fiber AB only, that actually how the strain will be coming and what kind of deformations are there along that particular path. So strain in the component, or we can say the fiber of AB, which is nothing but equals to change in length divided by original length, and the final distance of or final length of this fiber AB is A dash B dash. Earlier distance, or we can say earlier length of the fiber AB was AB, so A dash B dash minus AB divided by AB. So that means you see whatever the original path is there, means how much deformation is there divided by how much original length is there, this will give you the total component, means how much deformation is there, and this deformation generally we are measuring in terms of the strain. So strain definition is like that, but as far as the neutral axis is concerned, we already assume that the AB is equals to CD, because you see like there is a straight part when there is no bending moment is there, the straight regions are there, so AB is just cutting exactly as the CD. So there is no difference in that, same distances are there. So because there is no bending moment, there is no deformation is there in that particular like either the neutral axis and above. So we have AB equals to CD, but CD equals to C dash D dash, because the main thing is that the CD and C dash D dash are the points which are always lying on the neutral axis, and as we like we know that there is no strain or there is no deformation is coming on this particular neutral axis. So we can straightway like conclude that whatever the distance is there before bending moment applied and after bending moment applied on the neutral axis, they have the same distance without any deformation or without any strain. So we can say that CD is equals to C dash D dash, and if we apply those things here, what we have the strain component is nothing but equals to A dash B dash, which is the previous thing, and AB is equals to CD and CD is equals to C dash D dash. So we have A dash B dash minus C dash D dash divided by C dash D dash. So now you see here our main conclusion for the strain component is just focused on what will happen when the strain component is there. That means you see A dash B dash is nothing but the total deformed part at the along the line AB. C dash D dash is the new location for the points on the neutral axis, and you see like when both are comparing, then we can get the strain component. So since CD and C dash D dash, as I told you like they are on the neutral axis, and it is assumed that the stress on the neutral axis is always you see lying 0, and since there is no stress component is there on that particular part, so there is no strain, no deformation is there on that particular part. Therefore they won't be having any strain component on the neutral axis, and there is no deformation is there, so we cannot measure anything. So whatever the points are there before bending moment and after bending moment, they have the equal distances on the neutral axis. So for that now our main intention is to find it out with the using of the curvature theory, that what will be the distance of A dash B dash and the C dash D dash, so that we can straightway get the strain, and once you have the strain, then you can easily go with the stress component with the using of the modulus of elasticity, because whatever the deformation which we are assuming for this particular kind of analysis is always the elastic deformation, and all those Hooke's law is valid for that, and you see all those elastic modulus of Young's modulus of elasticity, or what are the components which are valid for the elastic deformation, they are also valid for this kind of analysis. So, come to the main point, that the strain is nothing but equals to A dash B dash minus C dash D dash divided by C dash D dash. So, if you focus on the A dash B dash in the previous diagram, then you will find that the total distance for A dash B dash was r plus y, and now you see this is the curvature path was there. So, into if you multiply this arc into this particular theta, then you have the total distance. So, r plus y into theta, that is A dash B dash minus C dash D dash is straight way, you see it is on the neutral axis where the distance is r. So, r theta will give you the total distance. So, r plus y into theta will be the A dash B dash minus r theta is the C dash D dash. So, if we put on these things in this particular formula, the strain formula, then we have r plus y into theta minus r theta divided by r theta, and if we generalize those things, then we have the strain is equals to y by r, where y is the distance of the fiber from the neutral axis. So, you see here always it is above the the neutral axis, and you see we just want to observe the effect of this bending moment on those fibers from the neutral axis, they have the distance of y. So, now you see, as I told you, that it is the elastic deformation where the Hooke's law is valid. So, we can again use the stress is proportional strain, or you see stress by strain will give you the Young's modulus of elasticity E, and then you see if we are keeping those values there, then what we have, this stress, the sigma is always denoting the stress. So, sigma by E will give you the strain, and you see in the previous formula we just derived that the strain is nothing but equals to y by r. So, we have the now real formula, and which is the basic formula for any bending stresses which are occurring in the like any beam kind of, you see irrespective whether it is a cantilever beam or simply supported beam, the bending stress is sigma divided by E, which is equals to y by r. Or we can say that the this bending stresses sigma is nothing but equals to y by r into E, or we can say that actually the E, which is the Young's modulus of elasticity, r which is the radius of curvature, into if you multiply the y. So, as y is just increasing, definitely you have more bending stresses, obviously we have, because you see if you just compare the realistic way this bending of beam, then you will find that the upper surfaces, because as you are moving from upper direction from the neutral axis, you know that we have more and more stresses, and this will conclude from this formula also that sigma is equals to E by r into y. So, as you increase the y, again you have more and more bending stresses in that particular beam. And whatever the fibers are there, the extreme corner, they are experienced with the maximum bending stresses in that particular way, and we will describe many more things in the further lecture. So, you see here now again if you focus on, now our focus was there, you see on just a distance at y, but if we cut the section of you see dy at this particular y. So, you see we have a just unsymmetrical section, and this you see for that we have a neutral axis for which is passing from this particular way, and we have a segment for which actually our main study is focused, that we have this particular small segment, and it has the total width is dy, and which has a distance y from the neutral axis. So, now you see what will happen when the bending moment is applied on that particular section, and how you see the area will affect of that. So, considering this particular arbitrary cross section of beam, as like we shown in that main, you see now what will be the strain on the fiber at distance y. That means you see what will happen when you see the bending moment will apply, how these fibers will play under the action of this bending moment, and then you see again we would like to start from the same formula, that when it is under the action of bending moment, then we have the bending stresses sigma, which is equals to E by r into y. And you see if the shaded area, which I just shown you in the dA, now if our main focus is on that what will happen when you apply the bending moment, then how fibers will play their key role in setup of the bending stresses in this particular strip dy. So, for that you see again our main focus is that actually what will be the force on that particular strip. So, the force is nothing but equals to whatever the stresses are there into the area, and area we consider dA. So, sigma into dA will give you the force, or we can say sigma, since already we have described that when it is under the action of bending moment, the bending stresses are there. So, sigma is the bending stress, and which is equals to E by r into y into delta A. So, now you see here we have the force. Once you have the force, then you can easily get the moment for those things. So, for moment about the neutral axis, this will give you force into the distance, because you see what we are doing here, we are simply taking a strip which has a distance y from the neutral axis. So, we can easily compute the moment like along with this particular neutral axis, because we have a distance. So, when we apply the force and the distance is there y, this will give you the moment. So, F into y will be the moment, or you see once you have the force, you can easily replace that force which is equals to E by R y into del A into, you see, the distance is y. So, what we have the moment which is equals to E by R y square del A. So, now you see if I just want to compute the this moment for whole of the section, because till now you see we discussed about a small strip which has like the area, elemental area dA, and which has the total like the width of the strip is dy. So, for that you see this moment is there which is equals to E by R y square into del A. But now if we sum up all those small element which has a distance, you see certain distance from the neutral axis, and if we like sum up with the summation this thing, we have the total moment which is there like moment applied on that particular section, and due to that we have the bending stresses. So, for that this total bending moment over the cross section is summation of E by A y square dA, or since the total summation is always focused on y square into dA. So, E and R are the constant one, as we discussed. E is the modulus of elasticity, which is a property of the material, what material which you are using. So, Young's modulus of elasticity will come, and the curvature is always focused that actually what the dimensional parameter which we are using for that. So, if you just take it out once, then we have, you see, the summation of y square dA is the total like will give you, when you sum up those things, the small element, it will give you a real feeling about the moment. So, once you do that, then you have the total moment for that section. And you see in this there are two component, one component E by R which as I told you, it is subjected to the like what kind of material and the dimension which you are using, but the another component in that is the summation of y square dA. This is a specific property, and this property like of a material is known as the second moment of area. That means you see like it is the very different thing is there, because it has the square term y square and it has area term. So, you see here we are saying a different way, not you see first area, it is the second moment of area of the cross section, and generally we are denoting I. So, I is equals to summation of y square dA. So, now if you are keeping those things, then we have the total moment m is nothing but equals to E by R, that was the first component. Second component, that was the summation of y square dA, which we replaced by I. So, we have the new equation of bending for like any kind of cross section, which is equals to m by I is equals to E by R, and like E by R we have already concluded that sigma by y is there in the first equation. So, the total like the bending equation for this, the generalized bending equation I should say, is nothing but equals to sigma by y, which is equals to m by I, which is equals to E by R, in which the sigma is the bending stresses which is coming due to the bending moment, and this bending moment is m, like which is always applied at the extreme end, or you see because due to the couple also it can be formed. Y is the distance which like the fiber we can say, or which we just want to find it out this bending stress, and the distance of that fiber from the neutral axis is y. So, this y is there. I is as I told you that it is the second moment of area, which is nothing but equals to summation of y square dA. So, one can easily calculate those things, and E is the Young's modulus of elasticity. It is specifically like the property of a material, that which material which you are using for that elastic property is there, and R is the radius of curvature. So, with all these 6 points or all these 6 properties, we can easily describe a generalized theory of the bending. Sigma by y is equals to m by I, which is equals to E by R, and it is a very good like the equation for solving many of the numerical problem, and this equation is known as the bending theory equation, a generalized bending theory like that. So, whatever the structure which we are using, it is, if it is under the action of bending moment, then this equation is valid if we are considering the deformation up to the elastic one. So, the above this above proof like has involved the assumption that pure bending without any shear force being present, because you see like we have sigma, that is the bending stress, m is, which is the bending moment, and you see other sections are very simply the dimensional parameters are there, like the y, I, e and r, and e is nothing but the property of material. So all those components, if you conclude, then you will find that there is no other stress component is presenting, only we have bending moment and the bending stresses, and that is why you see we can say that when the pure bending is there, there is no shear force is occurring within that. Therefore you see this term as the pure bending equation, as we discussed, and this equation gives the description about the stresses which are normal to the cross section, that means in the x direction. So that is why you see all these normal stresses are there, as we discussed that whenever a bending moment is there, they have the tensile and the compressive stresses, they are the normal stresses, or we can say that they are the flexural stresses. So this theory, which is known as the pure bending theory, has only the component related to the bending moment, bending stresses. There is no shear component is occurring in that. We have the normal stress component along with the bending stresses. So now you see in that we found that there are some special component within this particular structure. So we would like to first focus on those components. First is the section modulus. In that you see from the simple bending theory, this whatever we discussed in the previous equation, sigma by y is equals to m by I is equals to E by R. From that equation you see now our main intention is that when there is the bending moment is applied on this particular beam, then which area is influenced by the maximum bending stresses or the minimum bending stresses. And so for that you see here the simple case is just gives you that the maximum stresses which can be obtained at any cross section, sigma maximum, that is the bending stress maximum, is equals to m by I, whatever the bending moment which you are applying. I is nothing but the summation of y square dA. So these are the constant moment, but the key feature is that this distance y maximum. So means you see where this maximum bending stresses are occurring, means which fiber is experiencing this maximum bending stresses, which can be easily calculated once you know the maximum value, or once you know the location you can get the maximum value. So sigma maximum is basically depending on y maximum, that is the distance from the neutral axis. So sigma maximum is equals to m by I y maximum. Second equation is that for any given allowable stresses, means you see we have these allowable stresses for the bending of beam, and for that you see we just want to find it out the maximum moment which is acceptable to any particular shape of the cross section. We can easily get, because now our beam can be absorb this much amount of bending stresses. So we can get, once we know that this is the allowable stresses for this kind of beam. So for that we can easily get the maximum bending moment, and the formula for maximum bending moment is nothing but equals to I by y maximum into sigma maximum. That means you see the I, which is having all the summation of the cross section, like say the summation of y square dA. But you see what will be the the distance of the fiber at which this maximum bending moment is coming. So first of all this y maximum, which will influence this m, and second is how much bending stresses are occurring on those fibers, the value of that. So that will also depending parameter is there for calculating the maximum bending moment. So you see m is nothing but equals to I by y maximum into sigma maximum. These formulas are very important to calculate the remaining parameter, because you see in the question they can ask you that okay, now calculate the maximum bending stresses. So for that first of all you need to obtain that what will be the y maximum is there. Once you know the y maximum, because other parameters are very constant, m by I. So you see first of all you need to locate the location y maximum, and then you can calculate the sigma maximum, that means the maximum bending stresses. Similarly you see you can also calculate the maximum bending moment with that formula, as I shown you, I by y maximum into sigma maximum. And the last one is for ready compression, whatever you see these compressions are coming in that particular curved beam of the strength of this particular beam of any cross section, we can simply give with some relation, and that relation is coming with the section modulus Z. As we defined earlier also that the section modulus is always computing the geometrical parameters, like you see if we know that this is the location at which the fiber is there which experiencing the maximum bending stresses. So once you calculate that one, and once you know that what will be the I is there, you can simply compute the section modulus, and then you see whatever the bending moment is coming, which is always maximum, focused on the section modulus into whatever the maximum stresses are coming. So if you conclude all that part, then you will be having m is equals to z into sigma maximum, where the z is the section modulus which is equals to I by y maximum. I is nothing but the second moment of area in which we can calculate the summation of y square dA. Y maximum is the distance from the neutral axis. So we can calculate all those things with the corresponding way. So, you see here we have three different ways to calculate either the maximum bending stress or maximum bending moment, or also you see with the using of section modulus we can calculate, you see how we can relate the maximum bending moment and the maximum bending stresses. Those issues are discussed here, because of like once you have the basic theory of beam, you know that actually because of the bending moment we have the bending stresses at different locations, but to get the maximum value or the minimum value we should first identify the location that which fiber is experiencing, like, because in that particular if you know the concept of the bending, then you know that we have tensile stresses, we have the compressive stresses, but we have some of the section which doesn't exhibit any kind of stresses. So, for within those limits, you see our main intention is to get that which fiber is experiencing maximum bending stresses, and what will happen, you see, once you locate that part, how we can relate, you see, with the maximum stresses with the or bending moment or bending stresses with the section modulus Z. So, all these relations one has to be remembered, and these relations are there in front of you. So, the higher value of Z, because now you see we have M is equals to Z into sigma maximum. So, M is straightway depending on the Z section modulus. So, higher the value of Z for a particular cross section, higher the bending moment is there, because it is directly proportional to that which it can be withstand for a given maximum stresses. That means you see if you want to find it out that what will be the bearing capacity of the beam is, first of all our main intention is to find out that how much the maximum value will come for the section modulus, and once you know the section modulus maximum value, you can say that yeah, we can go up to this much maximum, the maximum value of bending moment, and the corresponding change is there in the bending stresses. So, that is why you see Z, which is the section modulus, is a very important parameter to design this particular beam for loading conditions. And now you see we would like to put one theorem to determine the second moment of area, because you see in previous formula you will find that I is a very important parameter. So, our main intention is that how to find out those things, because practically you see if you are going for individual sections and then sum up is not an easy thing, because you see it is not we have simply linearly varying this uniform structure or any kind of this kind of structure is there in which we can simply put the integration from 0 to some value and then we can get. Here we have a different uniform section in which the different segments are there. So, it is not easy to get all those small segment area, this y square dA, and then get some of those things. So, here you see we need to go with certain theorems. So, here there are two different methods. One method which I just discussed, that there are two theorems which are helpful to determine the value of the second moment of area, and which is required to be used while solving the simple bending theory of the equation, the integration of y square dA. So, first is summation of y square dA, second is integration of y square dA. Which one is helpful in which condition? This is the prime the matter of concern. So, first of all we first focus on the second moment of area, in which taking an analogy from the mass moment of inertia, as we discussed in the previous case, the second moment of area is also defined as the summation of area times distance squared from the fixed axis, because you see here what we have the y square into dA. So, first we need to calculate if we are taking any small segment, so what will be the area of that segment. Once you know the segment area, then how much distance is there of that particular segment from the neutral axis, square the term. So, y square into dA will give you this property arises while we were deriving bending theory equation, and this is also known as the moment of inertia, because you see here we are using the same concept of the mass moment of inertia, in which we are taking individual sections and sum up those things. So, here also this can also say that it is the moment of inertia in which we are calculating the same concept. An alternate name given to the second moment of area, because the first moment of area is different than second. First moment of area is the sum of the area times their distances from the given axis. So, if you are if you are summating the summation y into dA, that is your first this moment of area, but we are saying that the second moment of area, and because here we are multiplying this first moment of area into distance, or we can say that we are doing the summation of y square into dA. That is why we can say that it is the second moment of this area, or we can say that it is a moment of inertia. both have the same meaning, only our focus is that actually what we are doing, how we are dealing this problem, and what are the influencing parameter which are coming within that particular like things. So that's what you see, we need to cover those things. So for that, to calculate the second moment of area, again we are coming with the same structure, that we have any structure in which just the O is the origin, which is coming from the both of the axis, x to x dash, y to y dash, and then you see we have a small segment which we are taking, for which there is a small element dA is the area is there, and for that we have the distance r. So r can be like the polar coordinate is there, so it can be again related with the x to y Cartesian coordinate. So it has the distance x and y, so you can say that r is nothing but equals to x plus y, sorry, square root of this x square plus y square. And then you see once you focus on this like the small element of area, then once we have just the bending moment, and then there is a fiber which is influencing by the bending moment. So for this particular element area, how these fibers will deviating from their original shape under the action of this bending moment, it is a prime matter of concern. So considering any cross section having the small elemental area dA, we need to define that what will be the mass moment of the inertia is there, because what we are doing here the same as we discussed in the previous slide, that this, because we are summing up all those things, so it can also be known as this second moment of area is also be known as the mass moment of inertia. So Ix is equals to integration of y square dA. So in that again there is a term y square is coming, because it is the second moment of inertia, and dA is the total area which is our focused area in that. So if we focused on this the second moment of area, we would also always see that it is a kind of integration, because we have a regular structure. Now the moment of inertia about the axis which is like passing through the O, as like I just told you that x to x dash, x to x dash it is passing, or y to y dash it is passing from O, and perpendicular to the plane which like of the figure, like this one perpendicular to that is also called, you see, the polar moment of inertia, or polar moment of inertia is also like known as the area moment of inertia. So this is the new term is there, which is like the concern of area is just perpendicular to this plane of figure. So for that matter, you see, always whatever the second moment of area is coming, the new term is there for that, which is the Z, which is also known as the polar moment of inertia, and it can be like calculated, because it is just focused on this. We have the r, the distance for that which I shown you, this r distance from O to the our elemental area. So this integration of r square dA will be the equals to Z, or since r is nothing but was, you see, x and y was there, so r square is nothing but equals to x square plus y square into dA, or you see, if we segregate those matters, integration of x square dA plus integration of y square dA will give the new terms of the second area moment. So polar moment of area is nothing but equals to, we have this Ix plus Iy, or we can say Z is equals to Ix plus Iy. So you see all three, one is along the x axis, along the y axis, and the third one is just perpendicular to the plane of figure. All three like the this second area of this second moment of area is coming together, and this like relation is coming like due to that is known as the perpendicular axis theorem, and it is just stated like that the sum of the moment of inertia about two axes, x or y, whatever you see like which we are concerning here in the plane, is equal to the moment of inertia about an axis perpendicular to plane, that is the polar moment of inertia, that is Z. But condition is that all three axes must be like concurrent, that means they must exist together in the particular plane, so that we can say that Z is equals to Ix plus Iy. So this theorem is only valid when they are like concurrent, or we can say they are just existing together. So in that we can say that the Ix plus Iy will give you the Z value that is just perpendicular to these two plane. So you see here these two, the relations are there with the polar moment of area for that kind of section. But now you see here, if we focused on the circular section, so you can see the figure for a circular section, the polar moment of inertia can be easily computed in just similar manner, that again we need to just concern on the circular portion of that. So, what we have a circular portion having the diameter d, and you see our main focus is with the small this strip which has the thickness dr and which is located at the distance of r from the O. So, with that you see we can simply calculate the circular strip area dA, which is nothing but equals to 2 into pi into r into this thickness dr. So, 2 pi r will give you the total length whatever is there into dr will be the area. So, dA is equals to 2 pi r dr for the circular section, and with that now we know that the polar moment of inertia is nothing but equals to integration of r square dr, and now you have these the total symmetrical sections. So, for that we can simply integrate those things within those definite integral 0 to d by 2 or 0 to r I should say. So, 0 to d by 2 r square into 2 pi r dr, because of the small segment our main focus is there and which has a thickness of dr, small dr. So, this one you see that is what dA can be easily replaced by, as we discussed in the previous section, 2 pi r dr, r square is there, and since we are defining from 0 to r, so 0 to d by 2, 2 pi is the constant one, so it can be simply taken out from that. So, we have integration 0 to d by 2 r square dr, or we can say that 2 pi r since it is a cubic term is there from this multiplication. So, we have r to the power 4 by 4 0 to d by 2. So, we have the polar moment of inertia for circular section is pi d4 by 32, and it is just for since it is a perpendicular axis theorem it is coming. So, we can say that J is nothing but equals to Ix plus Iy, because we are simply concerning about the rth value, but in the previous section we found that when all three axes are existing together and you see they have the relation Ix plus Iy is equal to J. So, by applying those things what we have, since it is a symmetrical section of both the thing, Ix and Ir always must be equal to the moment of inertia about this particular diameter, because we are simply concerning about a symmetrical geometry. So, for that we can say that whatever the Ix and Iy is coming, they have the equal value. So, I diameter, because we are considering about the diameter, so I diameter is equals to J by 2, or we can say that the I is equals to pi d4 by 64, and this for this is for the solid circular section in which we have the radius r, or we can say the diameter is d. So, for that we can simply calculate the value of the second moment of area, that is I is equals to pi d4 by 64. But if we have a hollow section in which there are two diameters, the capital diameter, the outer diameter, and the small d is the inner diameter. So, if we have this kind of thing, then we can calculate the this J, that is the polar moment of inertia, is nothing but equals to pi d4 d to the power capital D to the power 4 minus small d to the power 4 divided by 32, or we can say the I, which is the second moment of area, is nothing but equals to pi d to the power 4 minus d to the power 4 small d to the power 4 divided by 64. So, you see here these two formulas are very important for solid as well as the circular shaft, because once you know the value of J and I, you can easily calculate the different property described for the beam, because you have the circular cross section of the beam, and you see all those properties, the bending stresses, the bending moment, they are absolutely focused on what the values of their of I and J. So, for that you see we need to calculate those things, and for calculation of I and J, the parallel axis theorem was very important, the perpendicular axis. Now, you see we have the next theorem, that is the parallel axis theorem. So, in that the moment of inertia about any axis is equal to the moment of inertia about a parallel axis through which is passing through the centroid plus the area times square. You see whatever the integration of area into distance whatever is there between the axis. So, you see this kind of theorems are always useful if we want to find it out the moment of inertia at a particular section of this the total object, because you see here we know the distance. Once you know the distance, multiply the distance by the area, you have one component, and then you see the moment of inertia which is for the axis which is passing through from the centered, or we can say the neutral axis. So, now you have the I plus integration of y into dA. So, this will give you the new moment of inertia about the particular axis. So, if in this particular diagram which you can see here, what we have a particular diagram in which G is the center of gravity through which we just want to find it out. If we are taking a small element, this one which has a diameter dA and which has a area dA and the distance is y is there from this axis. So, now our main focus is to find it out that at the ZZ dash in this particular section, what will be the moment of inertia, because we know this x dash and this moment of inertia, because it is passing from the centroid. So, it can be easily computed. Once you know these things, you know the distance, you can get the moment of inertia by this particular formula. So, here you see we have I x is equals to integration of y plus h this square term into del A. So, del A is the area, because our main focus is that one. So, with that, because here we are defining the moment of inertia about the axis z dash, because we know that x dash this moment of inertia can be easily calculated, because it is passing through the centroid. Now, what will be the distance is there? The distance we are assuming the h. So, with that y plus h into whole square, this y plus h whole square into dA will give you the iz. So, once you have the iz, again you can describe those things y square plus h square plus 2yh into dA, and since we know that y into dA, because you see y, it is nothing but like it is passing from that this centroid. So, y into dA integration will give you 0, because it is always, you see, there is no deformation is there within that particular element, because it is passing from the centroid. So, with that particular assumptions, now we have iz is equals to integration y square dA plus h square integration dA. So, integration dA is nothing but, you see, the total area which will give you. So, we have the A, and here you see integration y dA, which always we are saying that since it is passing from this square, it is a second area moment for the neutral axis, or we can say the centroid. So, it is I x plus A times h square. So, you see here we have, with the using of this parallel axis theorem, we can calculate this moment of inertia for any section which has a parallel relation from this neutral axis, or we can say the centroidal axis. So, for that iz is nothing but equals to Ix plus 8 area, which is the total area, into h square, and Ix is nothing but equals to Iz, as I told you, which is passing from the centroid, and A is the total area of the selection. So, this was there for a circular section. Now, if we have a rectangular section for this one, like if you want to calculate, so for that a rectangular cross section of beam, the second moment of area can be easily calculated for this. So, for that the diagram is pretty simple. We have cross section here, you see the rectangular cross section. This is, and for that the total distance is d in the vertical way, and the b is the width is there for this, and the neutral axis is passing from this, or we can say the centroidal axis is passing from this. It is showing by the dotted line, and our main we are taking a strip on which our main focus is there, which has a total width is dy in this particular direction, and the total distance of this strip from neutral axis is y, as we are using generally. So, with this configuration now, our main focus is to calculate that what will be the second moment of inertia is there for that. So, considering this rectangular cross section which has the area dA and thickness is dy, as we have taken, and the this breadth is b, which is located at a distance of y from the neutral axis. For that the second moment of area, this is I generally we are using, can be easily defined as we have defined already, that this integration of y square dA. So, with that you see like the moment of inertia at the neutral axis from minus d by 2 to d by 2, because you see the neutral axis is the centroidal part. So, it is coming from minus d by 2 to d by 2, like y square into b into dy, because this is the area, the width into the thickness of the strip. So, b into dy is the area, y square you see our, because it is a second moment of inertia is there. So, with that minus d by 2 to d by 2, or we can say that since the b is the constant one, there is we are not changing any breadth is there of this particular rectangular one. So, b is taken out. So, minus d by 2 to d by 2 y square dy, or we can say that the y cube by 3, and when we are keeping those things, we are ending up with the b by 3 d cube by 8 plus d cube by 8, or we can say that when we are calculating those things, we have d cube by 4 and outside is 3. So, we have bd cube by 12. So, here what we have the second moment of area about the neutral axis is bd cube by 12, when like the neutral axis is just passing through like the centroidal part, and distance is this d, and this is the width. And if we are changing those things, because if we are taking like the neutral axis which is passing from the b, and the d is parallel that, again you see this is a very special case. You see here in this case what we assume, we are taking like the dimension, that diameter is this, and the neutral axis is just cutting the diameter in this way, b the width is parallel. For that you see the second moment of area about this neutral axis is BD cube by 12. But in the other case, if I am taking the same this rectangular cross section and the neutral axis passing from the B, which is parallel to D, so in that case we have I neutral axis is DB cube by 12. So you see here we need to be very like cautious about those things, that what we are taking and how it will come. So you see again like what we discussed, that actually if it is passing from those things, then we have like the second moment of area for this particular rectangular section, which has the axis passing from the lower edge of the section. It can be easily found with the using of the same procedure which we have used from like 0 to D, or we can say minus D by 2 to D in the previous case. So for that we have I is equals to B y cube by 3 0 to D, since because we are concerning about the whole diameter from 0 to D1. So we have BD cube by this 3, because of that kind of cross section is symmetrical along the 0 to D diameter. These standard formulas prove very convenient like in determination of this second moment of area about the neutral axis I and A, to build up the section which can conveniently like divide into rectangular, because you see in the real structure what we are doing here, we have a different cross section. So we can easily divide into the rectangular shape, and then we can find it out the this second moment of area of along the neutral axis. And once you know these things, then you can apply the parallel and the perpendicular axis theorem to get the other this second of this moment of area at the particular section. And for instance like if we just want to find it out the moment of inertia about like the I section, then we can use like the above relation very easily, because I section is having like we have a first two rectangular section, and then there is a middle rectangular section. So it is you see two horizontal and the one middle. So how the compatibility is there, based on that we can easily get those value of I for those kind of sections. So now here you see we have a different structure altogether. Here we have like the neutral axis which is passing from the D. There are two different sections which has the same breadth small b, and the total b is this one. So as I told you, like if you want to find it out for a real structure, that what will be the like I and A is there. So for that kind of thing like it is just giving you like the small kind of gap. So the total the brick we can say, if you are using the brick or any kind of the rectangular structure, the breadth is BB for that, and the total breadth is capital B. The small diameter is D and the capital diameter is D for the whole section. For that we can calculate, you see the I and A, which is nothing but equals to I of the total this dotted rectangular minus I of the shaded area. So for this you see this there are two different shaded areas are there, and for dotted one this capital B and the capital D are the two main parameters. So BD cube by 12 minus 2 times of BD cube by 12 for a small section shaded area, or we can calculate you see the overall resultant from these two different kind of section which is coming in the this moment of second moment of inertia for this I and A is equals to BD cube by 12 minus BD cube by 6. So this is you see the resultant this like the mass moment of inertia for this rectangular cross section. So in this like lecture we discussed about mainly about like that what will happen when like a beam is there under the various kind of forces, then what exactly the relations are there when we are only talking about the bending like only, there is no other forces are there, only bending moment is there. Then you see what will be the relation like sigma by y is equals to m by I is equals to E by R. So this is the pure bending like the relation is there, the equation is there through which we can easily calculate the different parameters once we know the bending stresses or the moment, etc. In second section we discussed about the section modulus, and also we discussed about the second moment of area, that means you see integration of y square dA. So in these section we discussed about all like the basic concept of the bending stresses, like, but still we didn't discuss anything about when you see the bending moment or any bending stresses are there, along with that always there is a shear stress. So in the next section our main focus first is to solve some of the numerical problem based on these like the geometrical parameters and all those like the attempted values of these bending moment and bending stresses. So we just want to again use those like formula just to refresh our concept. So in the next lecture our main focus is to solve first the numerical problem, then the second section is like dealing with the shearing stresses, that when you see we have a bending moment with the shearing forces, then how these shearing stresses are coming all together with this particular bending stresses, and then what exactly the relations are there, and how the interaction is there in between these bending and the shearing stresses, and what exactly the relations are there in between those two stresses. That is our main focus. So in the next lecture we are going to discuss all these things. Thank you.
Thank you.